Suppose you want to understand the brain. The brain is an organ that thinks, but it's also a collection of cells that are like other cells in the body. And the problem is to understand the physics and biology of the cells and the collection of cells, and then relate that to thinking. This is a very difficult thing to do, and progress works best on the problem of understanding the cells, and that's where I concentrate my effort. The sort of research I do now is at a couple of different levels. One is to make detailed models of single neurons, and to make models of circuits of neurons, up to thousands of them, trying to figure out how the cells communicate with one another, either through conventional synapses or in unconventional ways, and then to relate that to experiments in vitro brain slices or in humans where we can observe population phenomena. For example, seizures, or so-called sharp waves, which is a very active area of research here in Berlin. Many years ago, my colleagues and I came up with a model of how sharp waves are generated that intimately and critically depends on so-called gap junctions between principal neurons. And many of the experiments which have been done here in Berlin support this model. If it's correct, it will be quite revolutionary in terms of how a very important population phenomenon in the brain is generated in a way that doesn't depend just on synapses. Why are mathematical models necessary? The systems we're talking about of cells and circuits are extremely complicated from a physics and engineering point of view. It would be like trying to predict the weather without mathematical models. I mean, the models we have aren't perfect, but without them, we cannot do weather prediction. The most direct applications of the kind of research I do for clinical work are in epilepsy. One of the practical questions that arises is, how can basic research into cellular mechanisms of epilepsy actually help epilepsy patients? So there are several ways that this can happen, and we hope will happen. One is a better understanding of how current anti-epileptic drugs work. Our knowledge about this is very incomplete, even for drugs that have been around a long time and which are often effective. Another way that basic research can help is in suggesting entirely new treatment approaches. For example, suppose it's true that the most important interaction between cells prior to a seizure is something different than what people usually think. That would suggest a whole new approach to treatment of epilepsy, and also to recording of phenomena that occur in the living brain of patients who are being evaluated for epilepsy surgery. My work depends absolutely critically on intimate collaborations with people who do real experiments and real biological preparations, or with patients. And the Einstein Stiftung has given me a wonderful opportunity that I absolutely depend on to come to Berlin and work with the very best people, not just in general, but the very best people who work in an area of direct interest to me. The Einstein Foundation has been extremely generous and flexible, and it allows a busy person to decide to pop over to Berlin at very short notice and stay for a short period, a long period, whatever works scientifically and whatever fits into the schedule. That's a wonderful way of doing things.